Okay, today we will talk about what is called the inclusion exclusion principle. And it is a counting principle which allows us to count numbers of various kinds of things. So, let us start by considering what is likely to be a very familiar example. So, here is the question. So, suppose you have a class of students . So, you are given this, and what is given, you are also given that everyone knows one of two languages, one or both. So, let me say at least one of two languages, let us say Tamil and English. Now, you are given how many know each. So, you are also given the following data, given that 30 students know Tamil, say 20 know English, and 7 know both languages. Now, the question is, how many students are there in the class? Okay, so you probably looked at questions like this before. So, what one could start out by doing is maybe drawing a Venn diagram. So, here is the Venn diagram. I will draw two sets A and B. Let us say A denotes the set of students who know Tamil. A is set of and B is students who know English, and we will try to use the given information to figure out what we can say about the number of elements in various portions of this set. So, the first thing that is given is that there are 7 students who know both languages. So, that is the intersection of the two sets. So, this region here which is shared between them has 7 students. So, that is what is given, A intersection B is 7. And what we could do is to try and figure out what the other regions look like. So, maybe here this is the part of A which is exclusively in A, not in the intersection. There is a portion of B. So, in a sense it split this set into 3 portions. Now, we can figure out how many there are in each. So, we know that the cardinality of A, total cardinality is 30, out of which 7 is in the intersection. So, the remaining 23 must be exclusively in A. Likewise, the cardinality of B is given to be 20, out of which 7 are in the intersection, and so similarly there are 13 who are exclusively in B. And the final cardinality, the number of students in the class. So, remember, every student knows one of these two languages. So, the set A union B must be all the students in the class. So, this is the full set of students in the class, because you are also given that every student knows one or both of these languages. So, what is the cardinality of the set A union B? It is the cardinality of these 3 regions added together, that is 23 plus 7 in the intersection and 13 on the other side, and well, whatever that works out to be, 43 in this case. But what we really want to do is to be able to understand how to get this answer more directly using the given pieces of information. So, what we are actually given are these numbers of elements in A, B and the intersection. So, let us just do the following, we will rewrite this as follows. So, I am just going to take this number 7 and sort of add and subtract it. So, I have 23 plus 7, I will add another 7 to it, maybe we will add this here plus another 7 plus 13, but since I added an extra 7, we are going to subtract that out, and now we will identify this with the given pieces of information. Now 23 plus 7, that is the cardinality of A, that is basically the exclusive part and the intersection. Likewise 13 plus 7 is the cardinality of B, and 7 is the part in the intersection. So what we have done is to prove this familiar statement, which I am sure you have seen, cardinality of A union B. We have split it into cardinality of A, cardinality of B, and subtract from it the cardinality of A intersection B. Okay. So that is what we have seen. Okay. Now how does one do this if we have more than 2 sets? That is really what the principle of inclusion and exclusion is concerned with. So let us just warm up towards the final form of the answer by looking at the case of 3 sets. So what if I had 3 sets A, B and C? So let us again draw a picture A, B and C. So this is sort of the most general situation. Now again, if you looked at it like we did before, how many different regions should we look at if we are looking at the set A union B union C? Well, there is this portion which is exclusive to A, portion exclusive to B, portion exclusive to C. Then there are portions which belong to 2 of these 3 sets A, B and C, and finally there is this last bit here which belongs to all 3 together. Okay. So we have actually split the full set A union B union C into these 7 regions, and one way of trying to find the cardinality of A union B union C is to figure out how many elements are there in all in each of these 7 regions separately. Okay, but we will try and do this similar to what we did before, which is to try and get the answer just using what is given. Okay. So what is given in this case typically will be the cardinalities of A, B, C, the cardinalities of A intersection B, B intersection C, C intersection A, and the cardinality of all the intersection of all 3 together. Okay. So here is the problem statement. We would like to compute the cardinality of the union given the following pieces of data: cardinalities of the individual sets, cardinalities of pairwise intersections, and the cardinality of the threefold intersection, all 3 together. So if I give you these 7 pieces of data, can you use them to find the cardinality of the union? So that is the question. Okay, now let's try and do this. So what is I'll try and pictorially depict each of the pieces of information we are given. So firstly, cardinality of A. So let's circle that. So I'm going to try and understand what cardinality of A means. Being given the cardinality of A means I am given the total number of elements which lies in this region, and in this region. So these 3 together give me the cardinality of A, right? One more, this region. So these 4 give me the cardinality of A. Now if I look at the cardinality of B, likewise I have to look at this region, this region, this region and this region. The cardinality of C, let's color it differently, blue, this and this. Okay, so I have gotten ABC. Now let us look at twofold intersections. So, let us look at cardinality of A intersection B. Now, that is going to be let us see. So, I know what A intersection B is. So, that is this region here. So, this whole region is A intersection B. Now, let us see what is it that we are looking for finally. We want to find the cardinality of just the union, which means we want to sum up the cardinalities of each of these 7 regions separately. Okay, so the principle of inclusion and exclusion, when we have 3 sets, takes the following form. If you want to find the cardinality of A union B union C, you start out by approximating it in some sense by the sum of the cardinalities of the 3 sets, but that is usually too much. So, what we do is from that we subtract the cardinalities of the pairwise intersections and at the end we just add the cardinality of the threefold intersection. Okay. So, let us try and understand this. So, for contrast, remember how did if you only had 2 sets, the cardinality of the union was minus the cardinality of the intersection. So, here we also have threefold intersections. So, it takes this form. So, let us try and understand this term by term or prove it term by term. So, what does cardinality of A mean? Cardinality of A is the sum of the total number of elements in these 4 regions, right, because that is really together they form the set A. Likewise, the cardinality of B will be the sums of the cardinalities in these 4 regions. C will again be these 4 regions. Okay. Now, having done that, what are we doing next? We are trying to subtract from that. We are going to subtract the cardinality of A intersection B, which means we are going to subtract out the, so I am going to put a minus sign now to say I am subtracting the number of elements in those 2 regions. B intersection C similarly, let us use a different color. B intersection C is these 2 regions, and C intersection A is C intersection A will be these 2 regions. Okay, and finally, A intersection B intersection C, that is the region that is contained in all of them. So, I have put pluses and minuses to keep track of what I am doing on the right hand side of this formula. Now, let us look at what the final collection of pluses and minuses looks like. Okay. So, the regions which are exclusively in A, B and C, they just have one single plus sign. Okay. So, those 3 terms are, I mean the elements in those 3 regions are just being counted once with a plus sign. Now, if you look at elements here, so I have got a plus and a minus. So, so they are being counted once with a plus sign and once with a minus sign. So, that just means I can erase that plus with its minus. So, what I now have is regions which are in the region A intersection B, which is not in the intersection, that also gets counted with a single plus sign. Now, let us keep doing the same thing everywhere. I have got a plus here with a minus. So, that means this is counted with a single plus, plus minus, single plus, and now the region in the middle is a mess, but let us look at it. There are 4 plus signs and 3 minus signs. So, which means I can remove all of these and be left with just a single plus sign. Okay. So, once you have done this process, so I have just looked at what the right hand side looks like. It just gave me every single one of these regions. Remember, there are 7 regions. Every one of the 7 regions just got counted once with a plus sign. Okay. So, that is the proof, because when you add up the sum of the number of elements in each of these 7 regions, it exactly gives you the cardinality of A union B union C. So, this is nothing but sum of cardinalities of the 7 subsets or 7 regions. Okay, and that is exactly what the right hand side is counting, even though it is doing it by a complicated sums of pluses and minuses. Okay, now that's the inclusion exclusion principle with 3 subsets. Now before we look at the more general version, let us do an example. So what I am going to do is to use this to count prime numbers. Okay. So here is the problem, how many composite numbers, so recall composite just means it is not prime and not 1 also. So how many composite numbers are there between 1 and 120, including both. So let me say in the set of elements 1, 2, 3 till 120. Okay, I could ask this question differently, how many prime numbers are there between 1 and 120? Once I know one, I know the answer to the other. Okay, so let us try and see what this has got to do with the principle of inclusion and exclusion. Now when we talked about prime numbers and Euclid's algorithm and so on, one of the things we observed is the following: if n is a composite number, suppose n is composite. Now what that means is that it can be written, it has got factors other than 1 and itself. It can be written, for example, as a product of 2 numbers a and b. Both a and b are numbers which are strictly smaller than n. Now this implied in particular that one of these 2 numbers is less than or equal to the square root of n, right. This was one of the observations we made. So observe, if we do this, then this means that the smaller of these 2 numbers, so let me assume that a is the smaller of the 2. Okay. If b is the smaller, I will just do the same argument with b instead of with a. So let a be the smaller, then observe that a has to be less than or equal to the square root of n, right. And how did we argue this? We said if if this failed, that means a is bigger than square root of n, but b is bigger than a, so b is also bigger than square root of n, and their product a times b therefore would be more than square root of n times square root of n, which is n. So that is where you get the contradiction from. Okay. So what does this mean? That if therefore if n is a number between 1 and 120 is a composite number, if n is a composite number, then it means that n is divisible by some number smaller than its square root. Okay. And in fact, if it is divisible by some number, it is also divisible by a prime number, by a prime p which is smaller than or equal to the square root of 120, and observe square root of 120 is smaller than 11. So there is a prime p there exists. So let us finally write down the conclusion. There exists p prime, p at most 10 such that p divides n. Now what does that mean? We know the primes which are at most 10, so therefore p can be 2, 3, 5 or 7. So we have concluded that when you are looking for composite numbers between 1 and 120, what you are looking for really are numbers which are divisible by one of these 4, 2, 3, 5 or 7. Okay. Now let us see how would we find out how many numbers between 1 and 120 are divisible by these. So let us simplify matters a little bit. Let us throw out all the even numbers. So first simplification, how many even numbers do we have? Well, there are 120 by 2, which is 60 even numbers. Okay, out of these Well, even numbers are always composite except for the even number 2 itself, which is prime. Okay. So, these except the number 2, all others are composite. So, there are 59 composite even numbers. So, that is the first observation. Therefore, there exists 59 composite even numbers between 1 and 120. Okay, so everything is only in the list of numbers from 1 to 120. Okay, so those are done. Now we are going to look for the composite odd numbers. So let us look for composite odd numbers between 1 and 120. The observation we just now made says that if n is a composite odd number, then it means that n is divisible by 3, 5 or 7. Okay. So, let us write the statement here, n from 1 to 120 is a composite odd number is the same as saying, so it is if and only if n is a multiple of 3, 5 or 7. It can also be multiples of more than 1 also, that is all right. Okay, so that is the observation. So now we are down to trying to calculate how many multiples of 3, 5 and 7 there are, but how does this fit into the framework of inclusion exclusion? So let us draw our 3 sets. So the first set we are looking at is A, which is all multiples of 3, B, which is going to be multiples of 5, and C, which are multiples of 7. Okay. So those are 3 sets. So let A be the set of numbers from 1 to 120 such that 3 divides n. B similarly, seven divides. Okay. Now observe, there will of course also be numbers in A intersection B, B intersection C, C intersection A, also in the threefold intersection and so on, right, because numbers can of course be divisible by both 3 and 5 for example. So what is it that we want to do? We want to find out how many numbers are there between 1 and 120 which are divisible by at least one of these 3 guys. Okay. So what we are interested in is the set A union B union C, which is exactly the set of numbers from 1 to 120 such that n is a multiple of 3, 5 or 7. Okay. Now that is where inclusion exclusion kicks in. So let us apply our formula. It says to compute this I need to know 7 other pieces of data. I need to know each of these cardinalities. But every one of them is actually easy to calculate. Okay. So let us do this in this example. Now how many odd numbers? So we will do them step by step. So first let us look at what is the cardinality of A. So this is the number of odd numbers. So remember A, B, C are all, oh I should have said odd numbers, sorry, let me change this here. N is, so A, B, C is all n from 1 to 120 such that n is odd, right. I already threw out the even numbers. So in all cases I am looking at odd numbers and I am looking at multiples of 3, 5 or 7. Okay, n is odd. Okay, so now let's try to find out the cardinalities of each of these sets. So how many multiples of 3 are there from 1 to 120. So 120 divided by 3, that is 40, I have 40 multiples of 3 from 1 to 120, right. What are they? They are 3, 6, 9, 12 and so on, but of course every alternate one of them is even, right. So I am only looking at the odd multiples. So out of this 40, there are only 20 odd multiples. So this is not cardinality of A yet. There are totally 40 multiples of 3, but what I want is only, so A, which is just the odd multiples, there are only 20 of them. So that is the first observation. So that is number 1. Second piece of data is how many elements of multiples of 5 there are. So again same computation, 120 divided by 5 will give me 24, but of these only half are odd, the other half are even. Okay, number 3. So I have 120 divided by 7, well that's going to be in fact 17, and so let us look at how many of these are odd, right. So what are the last multiples? So let us write it out, 7, 14, blah blah blah. So I have got 98, 105, 112 and 119. So that is the last multiple. So out of these 17 multiples, I have got 9 of them are odd numbers. Okay, so 17 total multiples of 7, but out of them, I mean half are odd, but starting with the very first one, 7 is odd, 21 is odd and so on, the very last fellow is odd. So in fact there are 9 of them which are odd multiples. Okay, so I have got cardinalities of A, B, C. Now let us look at the twofold intersections. So we need to look at cardinality of A intersection B. Now what does it mean to say something is an A intersection B? That means n is divisible by 3, n is also divisible by 5. Now observe that this can only happen because 3 and 5 are two different prime numbers. If 3 and 5 both divide n, this means their product, which is 15, must also divide n. Okay. Now therefore what are we looking at? We are looking at multiples of 15, that is what A intersection B would mean. So how many multiples of 15 will you have between 1 and 120? Well, that is 120 divided by 15, and that is 8. Now again only half of these are odd numbers, so A intersection B is in fact just 4. Okay. Now the others are very easy, similar, B intersection C and A intersection C. So B intersection C will mean I am looking at numbers which are divisible by 5 and 7, in other words numbers divisible by 35, and again when I divide 120 by 35, well 35 3s are 105, so it is 3 point something, so there are only 3 multiples of 35, and again the first and the third multiple, that is 35 and 105, are odd. Okay. Now likewise A intersection C is going to give me multiples of 3 and 7, in other words I am looking at multiples of 21, and again 21 5s are, so when I divide 120 by 21 I get 5 and something decimal. So out of these 5, 3 are odd. Okay, and finally what is A intersection B intersection C? That just means I am looking at n which is divisible by 3, 5 and 7. So 3 divides n, 5 divides n, 7 divides n. So this is the same as saying their product of all 3 divides n. So that is 105 divides n, there is only one such number which is 105 itself. Okay. So that is the entire computation. Now what do we have? We have all 7 pieces of data that we need to calculate A union B union C cardinality. Okay. So let us add and subtract these in the appropriate orders. So, let us see what A union B union C will therefore become. So, finally is cardinality of A plus the cardinality of B plus the cardinality of C minus we had A intersection B. So, it was 4 plus 3 4 plus 3 plus 2, okay, and then finally a plus a 1. Okay, so let us check that we got this right. 4, 2, 3 and a 1. Okay. Now, what is this finally? Well, that is 32, 41, then this is 7 plus 2, 9 plus 1. Okay, so that is 42 minus 9, so that is about 33 numbers. So, what we have is 33 odd numbers. So, that is our final conclusion here, that 33 odd composite numbers, okay, but not quite. So, these are 33 multiples that we have obtained of the numbers 3, 5 or 7, but of these 3, 5 and 7 themselves are not composite, right. These 3 guys are actually prime. So, we have to subtract those 3 from this total. So, therefore, out of these 33, 33 minus 3, which is 30, are odd composite numbers. Okay, so final conclusion is the following: there were 59 even composites and 30 odd composites, which is a total of 89 composite numbers between 1 and 120 and between 1 and 120. Now, of course, we can ask the corresponding question for primes if you wish. Out of the total 120 numbers, 1, recall the number 1 is considered neither prime nor composite. So, I also have to get rid of 1. So, the number 1 is neither prime nor composite. So, that is 89 numbers composite, 1 number which is neither, so that leaves 30 numbers. So, 30 numbers between 1 and 120 are prime. Okay. So, what we have actually done is computed the total number of prime numbers from 1 to 120 just using very minimal information. We did not actually write out all the prime numbers in this case.